There's now some time for general discussion, and I'm being told that it's done by Shang-Pei and Richard. Here's a mic, you do what you want.
Unfortunately, we don't have Piero here, so I don't know if Piero's here, so it would help. Considering that a lot of things I would be discussing are regarding reionization. So do you have... So I have a bunch of questions I came up with from various talks, but how much did you put together some? I put together some slides which basically pose various questions.
No, I didn't prepare any slides, but I think we should just encourage more comments from the audience and questions for the afternoon session. I think there was more time for discussion this morning, but go ahead.
Okay, well, I'll just I don't know if I'm unique. We need the mic, but let's see. Where's the? Okay. Oh, it is. Okay. Yeah, they're recording this necessarily. Well, I'll just bring out some various questions and topics, and I know that Pierre would respond to all these comments, but maybe Martin has some opinions on these. Handel has some opinions on these things as well. I think there's a few points where is Brant here anymore? Okay. Yeah, all the people that I was hoping to provoke with various comments seem to have evacuated the room.
This isn't coming through. Try this one.
Okay. Yeah, that's. Hoping to have experts here, so. Okay. So yeah. So I was just had a few. So major topic discussion this morning was basically reionization of the universe, and so I felt like there were a lot of questions which arose, at least in my mind, regarding each of these as viable solutions, and some things that basically evolved through the discussion. So one thing, if galaxies are going to be a viable solution to solving reionization, one important thing that we need to understand is regarding how the escape fraction evolves with time. And so there's a lot of other very circumstantial evidence suggesting that it definitely evolves with time, at least from low redshift to high redshift. The Lyman alpha escape fraction definitely evolves, pretty well known to evolve from various work from Matt Hayes. And as Martin pointed out, and basically from between redshift 2 and 6, from various constraints in the Lyman alpha forest, it's very well known to evolve because the ionizing emissivity, or basically the ionizing background, is roughly, a lot of these things are sort of not evolving that rapidly with time. And so basically, I don't know if this is completely right, but basically a lot of these results would basically suggest that the escape fraction is basically 1 over this thing. So basically the escape fraction is roughly higher at redshift 6 than redshift 2. And so basically you'd expect that the escape fraction gets much higher as you go to higher redshift. However, if you just take the results at face value, the results I presented, and also basically you notice this very similar evolution of the UV luminosity density ionizing background, that would suggest that the escape fraction does not evolve beyond redshift 6 if galaxies do reionize the universe.
On the other hand, the clumping factor may evolve.
Yeah, the clumping factor may evolve, but the clumping factor is only a minor perturbation on this overall on the overall result because basically we're in a photon-starved situation. And since we're in a photon-starved situation, every hydrogen atom is generally only reionized once. So given that fact, basically given the similar evolution of these two things, it sort of suggests that the escape fraction would not evolve beyond redshift 6. And other people seem to find, basically, yeah, I showed this result here, but this is not too different from the evolution that Pierre or Brant Robertson finds. And if the same result is sort of implicit, many of you may be more familiar with this plant plot from Brant Robertson, but basically in this plot, basically this you see the star formation history, and basically in this plot, Brant suggests that the ionizing emissivity basically evolves very, very similarly to the evolution of the star formation rate density. And basically he's suggesting that it agrees much better than it would have agreed with W map. So, yeah, it's 20%. And he basically just sets them equal to each other.
So to me, the newest thing that I learned today is that on the pyramid, 20% utterly incompatible with those elections.
Yeah, that's right. That's right. I mean, I had a few slides back, and I'm not sure it's totally accurate, but basically, at lower redshift, it definitely has to be closer to 5% or less. And if you include, it depends on what contribution you assume from quasars, but the more quasars contribute, the less it has to be.
So therefore, you take that at face value, this is just
Yeah, so basically what Brant, I mean, this is implicit in both my results and in my results. Well, obviously they're using the same data, but basically in all these plots, beyond redshift 6, the assumption is that the escape fraction has to be constant. Otherwise, everything would match. And which is a bit strange given the fact that there's such huge evolution there would have to be such huge evolution between redshift 2 and redshift 6. And I guess Piero's not here.
But to Frank's question, I mean, we're talking two different galaxies, and it's just very massive and
Well,
solar mass halos. But organization, you're talking about 9.
well, but even at the faint end of even at redshift 2, there's a lot of UV faint galaxies as well, which will also contribute a lot to the luminosity density.
Yeah. On the observational side, there's a filter by Smith and they give much higher escape fraction.
Okay. No, it's definitely well it's I think that's just for a few objects maybe, but I mean it can't be any higher than 5%. Otherwise you at redshift 2 to 3 overall, if you integrate overall galaxies, otherwise it will tend to violate various constraints.
He was talking about redshift 4 or 5.
Okay, but yeah, from 4 or 5, yeah, okay, maybe. But at redshift 2 to 3, it can't be more than maybe about 5%.
What would you need for this time evolution? Even the few galaxies that are not after this, I got the impression it's still a very, very deep clinical state and what the actual escape fraction is supposed to be.
Yeah, I think that's a really good point. Looking at the most playing a role using escape fraction.
So yeah, what?
I want to raise understand. If at least every one of these agrees that redshift 2 and 3 escape fraction, the average escape fraction of a galaxy for star formation use program must be less than 5%. Should I be puzzled that for AGN, apparently 100% AGNs are things that the densest regions of galaxies? How would the densest regions be at 100% of UV photons coming out of the outer space? We get 0% coming out. That to me sounds weird.
Yep.
The agents, we're looking at a professional argument. The agents, we can see the argument, we know we not make this will cover for a time. The right again, program just right think what the wafers do is they're so bright that you can ionize the plasma. Really need the phase. Where photons get out, so that time light phasor is the light phasor, so that the clear permanent light phasor to the time being.
What about type 2 wafers? Presumably, 2/3 of the 4 pi is covered by products.
So plastic phasors normally never put into this equation, so if something isn't right,
Is it UV bright?
so you only count the ones that actually are UV.
Yeah, I think the UV faint ones are completely different questions.
That's the good ones sort of don't contribute, because obviously
Yeah.
Or UV bright ones, only the ones that are already at it, looking down the
you don't quite know how large the problem is. Not so funny. You know,
Okay.
I just say, that simulation-wise, we have done careful work, including running with all the stars, and careful handling of certain feedback, set of exposing 4 phases propagation. We got about 15% simulation for galaxies in UV minus 6. Just right.
Yeah, just to continue on this point, basically, in terms of this is the ionizing emissivity here, and basically from Planck, if you just try to match all the constraints, you basically get a situation where the evolution of the ionizing emissivity looks very similar to the star formation history, as I just said, this basically assumes no evolution of the escape fraction. However, people like Pierre Madao, who say there's very strong evidence for evolution in the ionizing emissivity, the escape fraction between 2 and 6, seem to be much more comfortable with the WMAP situation, where we take the WMAP results at face value that suggests that the evolution of these ionizing emissivity is basically flat at high redshift, where you basically, which would be very different than the star formation history. So things would roughly go like this. And so in a way, I can't really, Pierre's not here to address this point, but just talking to him, it seems like Pierre seems like he might be more comfortable with the WMAP results, where essentially the evolution of the escape fraction would perfectly make up for the evolution of the UV luminosity density itself, so that you'd end up with a picture much more like this. So if the if the escape fraction evolves, then you end up having a ionizing emissivity or volume density of these ionizing photons, which is basically flat with time, rather than something that looks more like star formation history. So, okay, so that's all I wanted to say on that. There was something I thought that this sort of might be an interesting discussion point from some recent paper. There was this discovery of this redshift 8.7 object with Lyman alpha emission. Basically, so you see this Lyman alpha emission, this very high redshift object, and if you go to the Brandt-Robertson plot at redshift 8.7, the universe should be nominally basically 70% neutral by that point in time. And Martin showed a bunch of results from various simulations on what fraction of these Lyman alpha photons, what fraction of these very high redshift objects we might expect to find very strong Lyman alpha emission from. And I just wanted to know from Martin if he had any comments based upon this extensive work that his team has done, how he might interpret objects like this redshift 8.7 object.
I know many of them will find haven't heard problems already at redshift 10, maybe 12, 15. So if you say everywhere, find now suddenly Lyman alpha, so if you completely reverse the rapid evolution, then finding individual objects, I think we really have to start quantifying sort of the volume for the vector.
So you would.
So it's either ionized or not. So 70% doesn't mean that in every place 70% neutral. It means 70% of the volume is probably still neutral, but that still means 30% is ionized. There's a certain minimum size of the bubble so that you don't see the damping on the other side of the bubble. And sort of a few objects are not a problem, but if you suddenly sort of completely invert the amount of energies,
I mean, would you expect that much field-to-field variance? I mean, people have looked at a few fields and they haven't seen Lyman alpha at all.
Probably even more than the model can show, because discuss this large variation in the Lyman alpha capacity, and we directly see in the Lyman alpha capacity. That's exactly the stuff takes out the Lyman alpha and the other things. There might be another
Okay, yeah, so maybe I'll just, I don't have, I can just finish up.
just imagine a galaxy in the bubble of the quasar.
Yeah, so maybe I
Find
should.
a redshift A quasar, and then bubble you will see all the Lyman alpha.
Yeah, I probably should just, I can keep on going, or I could just let you go.
I would like to ask just a couple questions. There are only 5 minutes left. So what is the observation of the Congress today that we heard this morning that quasars may be making a comeback, and we've heard about observations. We heard of observations of faint AGNs and various maintenance mode and from the observers, but it's fairly striking that the simulators, except for the very last talk, turned off the AGN. We heard a lot of nice works on supernova, star formation feedback, and looking at the schedule, it appears that this theme is going to continue in the next few days. So, and since Roman was standing up, I thought I'd just give this chance to feedback, whether you can make some statements. General statement about where things are. I know it's a very difficult problem, and it may interfere or reinforce star formation. Roman, do you want to comment on where things are in terms of AGN simulations? Maybe you will talk about it on Friday. Could you summarize that quickly for us?
There's an honest answer.
So I think it's a very complicated question because we don't resolve the relevant scales. So now there are a lot of effort going on about trying to improve the realism of the interaction between the AGN and the environment. And I think Oriane gave a few examples of like actually physics inserted in the problem. And as far as I can tell, it's not really very efficient when it comes to the AGN interaction with the direct environment, the galaxy itself. Now you have a lot of issues about how you model the ISM close to the black hole. You have a lot of issues how you model the